Okay, now we're going to talk more in depth about water. Let's see, I can't really get my face too far out of the way. One of the things that we really need to look at is why water is so important. And it tells you right here that a lot of its properties come from hydrogen bonding. We've already discussed that. It's been a while though about what hydrogen bonding is. If you need a refresher, then you need to go back to chapter 8. But hydrogen bonding gives water something called surface tension, and you can see the definition that's the inward force or pull that tends to minimize the surface area of a liquid. If you have ever looked at a droplet of water, I don't know why exactly you would, maybe you were bored, but instead of just making a flat puddle, when you see water, it actually kind of makes a bulging drop, especially over on the sides. It almost looks like it wants to go over the sides, but yet it holds itself together. And it's because it has surface tension that actually helps pull the water in and hold it all together. Sorry, you're watching me do all this stuff. Some of the things that surface tension allows to happen is it allows bugs to walk on water, and it makes the droplets be like an actual drop and have three dimensions to it instead of just a flat puddle. And water has a really high surface tension compared to other liquids, which is actually really good for us in terms of life, because that makes it so that it can do things like have capillary action. It helps it to basically kind of climb itself up the veins of plants, and it helps it to not evaporate as quickly because of the hydrogen bonding. So it's really good for us. Something here is a surfactant. It's anything that will interfere with the hydrogen bonding and basically break up the surface tension. Soaps and detergents are really good at this. I'll see if I can demonstrate it for you once I'm in class. But for now, just knowing the definition is good. And then you have vapor pressure, and we've discussed vapor pressure earlier too. Remember, vapor pressure is the pressure of a liquid right at the surface that's made from the gas of the liquid as it evaporates right on the surface of it. Water has a really low vapor pressure because the hydrogen bonding makes it really hard for the water molecules to leave the group that's a liquid and escape and evaporate. And so because of that, when you and I walk outside, all of the water that's in us doesn't just immediately evaporate, and it turned out to be really good for living things. On a hot day outside, if surface tension was lower and the vapor pressure was much higher of water, then that means ponds and lakes and the ocean and things like that would also be able to dry up really quickly and evaporate, and that'd be really bad for all of the living things that are inside of it. Now we're going to talk about solid water. I might just make my face disappear here since I have to keep moving myself. Solid water, you know, is ice, and it's one of a few solids that will float in its own liquid. Most things will get more dense as they get colder, and they'll sink. Water does that up until about 4 degrees Celsius, and then it actually starts to become less dense, which is kind of unique. The reason that ice does this is because it makes like a honeycomb structure. As it starts to freeze, it arranges itself in a way that it can take in air in between the water molecules, and it makes it into basically a little float. The air makes it less dense, and so it'll go up to the top of the water. And that's important to life because it allows living things to continue to float around in the water underneath it, like fish. So if this didn't work, when a lake froze, instead of the top freezing, it would freeze on top and sink, and then the next layer would freeze on top and sink, and freeze and sink until it was just frozen from the bottom up, and you wouldn't have any living things in the water at that point. Ice melts at 0 degrees Celsius, which is actually a very high melting point for a molecule that has such a low mass. So that's good for us too, that it can stay frozen up until 0 degrees Celsius. And a considerable amount of energy is needed to make ice melt. That's good as well, because you don't really want water, which is a considerable component of living things, to be able to change temperature really, really quickly. We're going to go ahead and look at the next section too in one video. We're looking now at heterogeneous aqueous systems. The first two sections have been about homogeneous things. This is largely about suspensions and colloids. A suspension is not what you get when you're kicked out of school, but it's when you have a a mixture that is not a solution. Now, suspensions can be homogeneous, which means when you mix them up, all the parts can really look the same, but they'll settle out in the end. So if you leave them setting long enough, they can actually settle. You can have heterogeneous mixtures that are suspensions. They are capable of settling. The particles are much larger than those of a solution, which is why they can be easily filtered. A colloid is a mixture with particles that are spread throughout, so it's kind of like a suspension that's just permanently suspended. There's lots of examples that are here on this slide. I can show you some in class, but aerosols are a really good example of colloids. All colloids and suspensions do the Tyndall effect, and I'll have to show you an example of this too, but when you do the Tyndall effect, if you shine a flashlight through a bottle of a suspension or colloid, you can see the beam of the light. You can do this sometimes in your house when sunshine is streaming through the window, and you can see the beam of the sunshine, and you can see like all the little dust particles that are floating through it. That little beam of light is the Tyndall effect. You also see it with your car headlights when it's foggy outside. And as you're driving, you can see your headlights really, really well. Like you see the exact beam of them as they come out of your car. That's the Tyndall effect. So the Tyndall effect is actually a test that you can use to decide if something is a solution or a suspension or a colloid. In solutions, you won't get any kind of beam. So if you just shine the light through some salt water, you shouldn't be able to see the beam of light. You'll see the light on the other side, but you won't be able to see exactly where it goes. Brownian motion is what actually keeps a colloid permanently suspended, and it's just the chaotic movement of the particles, the idea that they're moving all over the place all of the time, and it's like juggling. It's constantly keeping the particles up in the air and keeping them from falling down. A little bit more about colloids is coagulation, and that's how you get the particles to come out of a colloid. Basically, lots of times what they use is ionization to do this. If you charge the particles, the colloids will absorb ions on their surface. So if you can charge the colloids, let's just say with a negative charge, and what that'll cause them to do is move apart from each other because opposites attract and like charges repel. And so that'll help them, stay a colloid. So if you make the particles a negative and you introduce a positive to the mix, you actually cause them all to clump together because all the negative colloid particles are going to want to attract to the positive that you introduced. And so you can do this in your home with like air purifiers. You have the ionizers that are on them sometimes. When you turn the ionizer on, what it does is charges all of the particles, and then it'll introduce a negative charge or like an opposite charge, and it'll make them all want to clump together. And so it helps get the dust out of the air. It's just kind of one little trick of chemistry that you can use to help clean up things. Here's some more about colloids. If you're doing this for subnotes, somebody needs to go to the PowerPoint and click on the video link right here if it actually comes up for I don't know if it'll let me switch off of the pen. Click on the link for emulsions. There you go. It should be a YouTube video if it doesn't block you. An example of an emulsion is mayonnaise. An emulsion is just two things that basically mix. It's usually for liquids in a liquid. There's some other examples if you go to this one. I believe it's a Mr. Wizard YouTube video with some examples of emulsions. And he has some examples that are like a gas in a liquid or a solid in a liquid and a liquid in a liquid. But it's a colloidal dispersion. It's usually two things that wouldn't mix on their own. Like vinegar and oil make mayonnaise, and they should not mix. You should just have one on top of the other. You add egg to it. An egg is called an emulsifier. It emulsifies it. What emulsifiers do, as you can see down here at the bottom, is that they cause things to mix together that really shouldn't. This is used very commonly in cooking. You do this in your kitchen sink when you wash your dishes, like when you put the dish detergent in there, it causes the oil and the grease to mix with water. They normally would never do that, but the soap is an emulsifier. The cool thing about it is that the soap has a polar end, which will attach to the water, and a non-polar end, which will attach to the grease, and it's kind of like a little linker that holds the two things together. If you're cooking, there's other things that do this, like xanthan gum and other types of emulsifiers that are commonly used to bind things together. And that's the end of what I have. If I haven't been here, I hope you were able to take okay notes. We can talk about any questions that you have later. And if this is homework, well, then it'll just be game on as usual once we get to class. Thanks for listening.